Welcome to this comprehensive tutorial on debugging performance issues in Java applications. Today, we're going to delve into the intricacies of performance problems, identifying their root causes, and applying effective debugging techniques. Whether you're a beginner or an experienced developer, this video will empower you with skills to enhance application performance. Before we dive into the technical aspects, let's outline what we will cover in this video. We'll begin with an overview of performance issues, followed by methods to measure performance. Then, we'll look at common performance pitfalls and how to analyze them using Java tools and techniques. Finally, we'll wrap up with practical examples and tips for ongoing performance monitoring. So, what are performance issues? Performance issues in software refer to situations where an application does not meet expected execution speed, memory usage, or resource allocation. Some of these include slow response times, high CPU usage, excessive memory consumption, or long garbage collection times. Understanding these problems is crucial for any Java developer. Next, let's explore methods to measure and identify performance issues. The first step in resolving any problem is understanding how to detect it. For Java applications, there are several key tools and techniques you can use. One of the foundational tools is Java's built-in profiling tools, such as Visual VM and Java Mission Control. Let's take a quick look at how to set up Visual VM. First, ensure you have JDK installed. Visual VM comes bundled with the JDK distribution. Once installed, you can launch it from the bin directory of your JDK. This tool allows you to visualize memory usage, current threads, and CPU consumption. Now, let's run a sample Java application to give you a practical example of using Visual VM for performance analysis. Here's a simple multi-threaded application that we will intentionally cause to perform suboptimally. Once you run this application, open Visual VM and connect to the running instance. You will see the CPU and memory statistics updating in real time. Pay attention to the thread activity, particularly the CPU usage and the active threads. You may notice some threads are blocked or taking longer than necessary. The next performance issue we might encounter is memory leaks. Memory leaks occur when objects are no longer used but are still referenced by other objects or classes. Over time, this can lead to significant increases in memory usage and can eventually cause the Java Virtual Machine, JVM, to run out of memory. In this example, the method createLeak continuously adds integers to the leak list, which results in unbounded memory consumption. When we run this code, monitoring the application in Visual VM will allow us to see how memory usage increases over time. To diagnose memory leaks effectively, we can use profiling tools to take heap dumps. A heap dump gives detailed information about the memory allocation of objects within your application. In Visual VM, you can do this by clicking on the Memory tab and then taking a heap dump when memory usage spikes. After obtaining a heap dump, you can analyze it using Eclipse Memory Analyzer, MAT. MAT provides great insights into memory consumption, including identifying objects that are taking up the most space and their paths from the root. This process is crucial in identifying objects that are kept in memory longer than needed. Now that we have a solid understanding of memory leaks, let's move on to another common performance issue: inefficient algorithms. Choosing a wrong algorithm or using a brute force approach can drastically affect performance. It is essential to always evaluate the time complexity of the algorithms you are using. In this example, we've implemented the bubble sort algorithm, which has a time complexity of O(n)². For larger datasets, this will become inefficient. Profiling the execution time of this code will allow you to observe how performance changes with varying sizes of input. To improve performance in such situations, look for alternative algorithms or data structures. In our case, using arrays.sort, which uses a dual pivot quicksort algorithm, can lead to a significant performance improvement. Now, let's discuss another critical area: thread contention and synchronization issues. When multiple threads need access to shared resources, contention can occur, causing threads to wait longer than necessary to execute. This not only wastes CPU cycles, but can also significantly degrade application performance. In this example, multiple threads attempt to acquire a lock and enter a synchronized block. Due to the sleep statement inside the synchronized block, only one thread can proceed at a time, leading to longer completion times. Monitoring thread states in Visual VM can help illuminate such contention issues. An effective strategy to reduce thread contention is to use finer-grained locks or concurrent collections. Java's concurrent package offers several classes like reentrant lock and copy-on-write array list for such use cases. Consider this alternative approach using reentrant lock. This alternative reduces contention and allows for greater parallelism by only locking the code path that requires mutual exclusion. Always strive for minimal locking and prefer higher concurrency where possible. As we move forward, let's talk about inefficient I/O operations. Frequently reading from or writing to disk can become a major bottleneck in your application. Here's an example to illustrate inefficient file I/O. In this code snippet, we read a file line by line, which can be inefficient for larger files. Instead of processing a file line by line, consider using streams and processing the data in chunks. Using NIO, new input output, can provide non-blocking I/O operations and better performance for handling file operations. It is advisable to use higher-level abstractions provided by Java when handling large amounts of data to optimize read/write performance. Lastly, let's discuss the importance of monitoring performance continuously throughout the application lifecycle. Performance debugging isn't just a phase, it's an ongoing process. Implement logging and metrics for key performance indicators, KPIs, so you can quickly identify and address performance issues as they arise in production. In this demonstration, we record and log the time taken to complete a simulated processing task. By capturing this kind of data continuously, it allows you to establish a performance baseline and quickly recognize when deviations occur. This practice helps ensure optimal performance throughout the life of your application. In summary, we tackled several performance issues today. We learned how to analyze thread contention, memory leaks, and inefficient algorithms, all important factors in optimizing Java applications. Remember the tools we used, such as Visual VM for monitoring and Eclipse MAT for analyzing memory, as these can be invaluable assets in your debugging toolkit. As you embark on your performance debugging journey, always remember that understanding the problem is half the battle. Measure first, then analyze, and only then optimize. Seek to continuously monitor and enhance the performance of your applications over time. Thank you for watching this video tutorial on debugging performance issues in Java. If you found this content helpful, please consider subscribing for more programming tutorials and insights, and drop a comment below with your thoughts or questions.